video, we have been introduced to the notion of differentiation of multivariable functions. And in this video, let us look at some algebraic properties which we have seen time and again while talking about continuity, limits, etc. in our calculus course. Also, in this video, I am going to give you a sufficient condition for differentiability of a multivariable function to hold, and I will finish this video with a couple of worked out examples. So let us start with some algebraic properties as I have just mentioned. So recall that whenever we talk about algebraic properties, what we are going to talk about is that if we have two differentiable functions, then whether their sum product or a scalar product is going to be differentiable or not, or in fact whether the quotient of two differentiable functions is going to be differentiable, and if they are differentiable, then what are their derivatives at a given point that we are considering. So let us start. So as always, we take a domain of a function. So D is a subset of R2 because we are going to consider functions in two variables. For differentiability, as I have mentioned in my previous video, that I need an interior point of the domain. So suppose that f and g are two functions that are differentiable in the at the point that we have fixed, and also let us take a real number r. So then what we are going to say is that if f and g are differentiable at the point x0, y0, the point that we have chosen here, then f plus g is going to be differentiable at x0, y0, and the derivative of f plus g, which is the total derivative of f plus g at the point x0, y0, which is, as you have seen, is exactly equal to the gradient of f plus g at the point x0, y0, is just the sum of the gradient of f at x0, y0 and gradient of g at the point x0, y0. Now, if a function is differentiable, so f is differentiable and r is a real number, then rf is differentiable at the point x0, y0, and a similar gradient formula comes here. And also, if you have two differentiable functions f and g which are differentiable at the point x0, y0, then what we are going to see is that fg is also differentiable at the point x0, y0, and the formula for the total derivative is a bit complicated, but it is also easy to derive from the notion that gradient of a function at the point x0, y0 is nothing but the pair fx at x0, y0 and fy at x0, y0, and we do know how to compute this partial derivatives and what are the product rules, what are the rule for adding up two partial derivatives, etc, etc. So let us look at a proof of this algebraic properties that we have just mentioned. So what is the main idea? The main idea is to make use of the increment lemma that we have just seen. So now what does increment lemma tell us? We know that f is differentiable at the point x0, y0, and by increment lemma we see that there must exist two functions f1 and f2 that are continuous at the point x0, y0, such that fxy minus fx0, y0 is written as x minus x0 times f1 xy plus y minus y0 times f2 xy. So similar thing happens for g. So here you get two functions that are continuous at the point x0, y0, and gxy minus gx0, y0 is written in an analogous way. So this is going to be something that is going to be very useful in proving those algebraic properties, and what we are going to do is as follows. So we first look at the sum of two differentiable functions which are differentiable at the point x0, y0. So in order to show that f plus g is differentiable at x0, y0, I need to express f plus g xy minus f plus g at the point x0 y0 as x minus x0 times h of, or uh, let's say h1 of xy plus y minus y0 times h2 of xy. So we have to express this difference in this form where h1 and h2 have to be continuous at the point x0 comma y0. But it is easy to see using the above two equations. If I call this 1 and call this 2, if I just add these two things up, then I immediately get a form like this. And you see that f1 and g1, they are continuous at the point x0 y0. So f1 plus g1 is also continuous at the point x0 y0. Similarly, f2 and g2 are continuous at the point x0 y0, and consequently their sum is going to be continuous at the point x0 y0. So this gives me the sufficient condition in increment lemma, and it shows that f plus g is differentiable at the point x0 y0. What is the total derivative? As I have just mentioned, it can be calculated very easily using properties of partial derivatives. So similar thing happens for the function rf, and I'm not going to do this in all the coding details, but let me work out the function fg. So what is fgxy minus fgx0y0? So this is nothing but fxy gxy minus fx0 y0 times g x0 y0. So what I do, I play a small trick here. So I write it as fxy minus f of x0 y0 times gxy, and I adjust whatever I have deducted with the second term. Namely, what I do here is the following: I take f of x0 y0 times you say this is gxy, and here it is going to be minus g of x0 y0. So I can now write this as x minus x0 times f1 xy plus y minus y0 times f2 xy. So this is only a matter of bookkeeping, but I chose to do this because I wanted you to understand how it is done or see how these things are done. So f of x0 y0 times, and this from equation 2, what do we get? This is x minus x0 times g1 xy plus y minus y0 times g2 xy, and now it is only a matter of clubbing the x minus x0 terms together, or the terms which has x minus x0 as a multiple together, and the terms which has y minus y0 as a factor together. So what do we get? So we get that this is x minus x0 times, so this is going to be f1 xy times g of xy, and here what do we get? Plus f of x0 y0 times g1 xy. So this is going to be one of our increment functions. Let me come back to this in just a moment. Now y minus y0, it comes with f2 of xy times g of xy plus f of x0 y0 times g2 of xy. Now once I have written all these things in this form, all I need to check is whether whether this whole term and this whole term, they are continuous at the point x0 y0. But you see that f1 is continuous at the point x0 y0. G, so g was what? G was a function that we initially started with. It is differentiable, so g is also continuous. We have seen using increment lemma, we had proved that a differentiable function is continuous. So g is continuous. So and f of x0 y0 is just a scalar, so it is just a real number g1 that is continuous by definition by our equation 2. So all these things are continuous, and by using the algebraic properties of continuous functions we can see that whatever is there in the bracket over here is continuous. Similarly, we can see that this term is also continuous at the point x0 y0. So what do we get is that for the function f g, these two functions that we have here gives me a pair of increment functions, and this shows that f g is differentiable at the point x0 y0. So we have made use of the sufficient condition for differentiability which comes from our increment lemma. Now let us proceed. So this is one another algebraic property. So if is not 0, so we have all the assumption that we had taken in our previous algebraic properties. So algebraic properties part 1. So what do we have? F is a function from D to R that is differentiable at x0 y0, and x0 y0 is an interior point, and of course D is a subset of R2. So if f does not vanish at x0 y0, then we claim that 1 by f is differentiable at x0 y0, like we have seen always while talking about algebraic properties of limits, continuity, etc. So a simple calculation shows us that this pair minus f1 xy divided by fxy fx0 y0 and minus f2 xy divided by fxy fx0 y0 gives me a pair of increment function for increment functions for the function 1 by f, and again using our increment lemma or the sufficient condition that comes from our increment lemma, we can claim that the function 1 by f is differentiable. As I have mentioned many a times in the previous slide, that computing the gradient is not a big deal. It follows readily from the properties of partial derivatives. Now let us look at some corollary. So first, if we have r a natural number, so then we can talk about gradient of, and if we have f a differentiable function, then first we see that f to the power r is also a differentiable function. So let me write down. So if f is differentiable at x0 y0, then f to the power r is also differentiable at x0 y0. This follows from the product rule. So from f I can get f square is differentiable. Using f square and f, you can see f cube is differentiable, and then this process go on inductively, and using the gradient formula applied r times, you will see that gradient of f to the power r at the point x0 y0 is given by r f x0 y0 to the power r minus 1 times gradient of f at the point x0 y0. Again, this also follows from the partial derivatives. Now let us combine everything together. So suppose that we have two differentiable functions, one is f and another is g, which is differentiable at an interior point x0 y0 on our domain, and g of x0 y0 is not equal to 0. Then we have seen just above that 1 by g is differentiable at the point x0 y0. F is differentiable at the point x0 y0, so is their product. So in particular f by g, is also differentiable at the point x0 y0. And if I want to compute the total derivative, we will compute it in exactly this way. This finishes our discussion on the algebraic properties. Now let me give you a sufficient condition for testing differentiability of a function at a given point. As always, I have a domain D inside R2 and x0, y0 an interior point of D. Now, the sufficient condition or a sufficient condition says that if the partial derivatives fx and fy exist on an open subset containing x0, y0, and more importantly, they are continuous. So, we have two conditions here, is that fx, fy must exist. Let me write colloquially near the point x0, y0. So this near means that it exists on a open subset containing x0, y0. So you can think of a very small open disk that contains x0, y0. So if x and if y must exist in that disk, and it is continuous at the point. So and both of them, fx, fy, are continuous. Fx and fy are continuous at x0, y0. Then the function f is differentiable at x0, y0. So we omit this proof and we look at some examples that you might be uh, eager to see now. So let us first consider an example. So fxy is a continuous function. So f is a function defined on whole of the two-dimensional Euclidean plane over R, and I have defined f of xy to be equal to 1. So you can replace this 1 by any real number c, and it will not change much. So we have seen that if f is differentiable, so what we are going to do is that we are going to check differentiability of this function at every possible points. Now suppose I fix a point x0, y0 in R2, and we are not required to check whether this is an interior point or not, because the domain of the function is whole of R2, so it must be an interior point. And then we have said that if a function is differentiable at this point, then we have to compute the partial derivatives fx x0, y0 and fy x0, y0, and this will serve as our alpha and beta that we have seen in our definition. So it is very easy to check that the partial derivative of f with respect to x at the point x0, y0 is 0, and similarly partial derivative of y at the point x0, y0 of the function f is also equal to 0. Now if we put in all the information in this limit, so f of x0 plus h, y0 plus k, minus f of x0, y0 minus, what do we do? Alpha times h. So this is our alpha in our definition, this is our beta in our definition, and we divide everything by the norm of this vector hk. So this is the positive square root of h square plus k square. So now you can see that this function is constant, so this will take 1 here, this will take the value 1 here, alpha as we have computed is equal to 0, beta we have computed is also equal to 0. Put in all the information and you will see that this limit is indeed equal to 0, and this shows that f is differentiable at x0, y0. But x0, y0 was not any special. You could have replaced x0, y0 by any x1, y1 or anything alpha, beta, a, b in R2, and the same proof will work, and this says that this function is differentiable on R2. So let us go on. We look at a somewhat more complicated function here. So again, f is a function from R2 to R, and I have fixed a point x0, y0 as per my choice. I compute what is fx of x0, y0, and this turns out to be 2x0. Fy at x0 y0 turns out to be 2y0, and then if I put all these informations together, we'll see that there are very nice cancellations that are occurring. So what is x0 plus h, f of x0 plus h y0 plus k? This is going to be x0 plus h whole square plus y0 plus k whole square. What is f of x0 y0? This is going to be x0 square plus y0 square that I have written down. What is fx that we have calculated? So this is nothing but 2x0. Fy, this is nothing but 2y0. So I have put in all the information that we have here to compute the limit. Now you will see that here you are going to get x0 square plus h square. So x0 square cancels with this x0 square, and 2x0h cancels with this 2x0h. Similarly, here what we are going to see is that y0 square from this binomial is going to be cancelled with this y0 square, and plus 2y0k is going to be cancelled with this minus 2y0k. So all we are going to be left with is the term h square plus k square. So h square from here, k square from here, and we have seen before in our lectures on limits that this limit is indeed equal to 0. So this function is differentiable at x0 y0. Just as in the case before, this x0 y0 is nothing special, and this worked for every possible choice of x0 y0, every possible point x0 y0 in R2, and consequently the function f is differentiable throughout the two-dimensional Euclidean plane. Let us now look at this function if xy is equal to modulus of xy. So now when we have talked about this function in single variable calculus, we have seen that this function was continuous, but it is not differentiable. But here something surprising is waiting for us. So let me check differentiability at the point 0, 0. So where the problem occurred actually in single variable calculus. So what is fx00? So we are going to follow the same procedure as we have followed till now in the last two examples. So first we are going to compute the first partial derivatives. So fx at 0, 0 turns out to be 0. Fy 0, 0 turns out to be 0. Put in all the information, all we will be left with is equal to limit hk tending to 0, 0 modulus of hk divided by h square plus k square. Okay, so now let us look at this. So we have modulus of this whole thing. So let me use a different color. So modulus of this whole thing lies in between these two quantities. First, it is bigger than or equal to 0 because this is a non-negative real number whenever we have taken modulus. And then observe that mod hk, modulus of hk, is nothing but modulus of h times modulus of k, and I could write modulus of h as under root h square, which is less than or equal to square root of h square plus k square. So what it gives is that this is less than or equal to k modulus of k times square root of h square plus k square. And now some cancellations happen and we are left with modulus of k. Now as we let the tuple hk tend to 0, 0, we see that modulus of k goes to 0. This is a constant function. If I take limit as hk going to 0, it will be 0 as well, and we can use our sandwich theorem, and this will give us that this whole thing that goes to 0 as well. So what we have derived is that this limit is equal to 0. Okay, so now let us look at some further examples, 3 of this, and finish this video off. So now let me work out this example. So fxy is equal to x. So let me check whether it is differentiable at a given point. So the idea that we are going to now use is increment lemma, but you can do it in any other way you want, but I just wanted to illustrate how increment lemma is going to be used. So fxy minus fx0y0 is nothing but x minus x0. So you can see that this pair of functions f1 and f2, where f1 is given by 1 and f2 is given by 0, these constant functions work as a pair of increment functions. So you can of course see that these constant functions are continuous everywhere. So what does this give me is that f is differentiable at x0, y0. So one could similarly define a function g of xy to be equal to y, and this will give me that this function is also differentiable at x0, y0. So you can check that here g of xy minus g of x0, y0 is equal to y minus y0. So if I take g1 to be equal to 0 and g2 to be equal to 1, then this function g1, g2 work as a pair of increment functions, and consequently g is differentiable at x0, y0. So this was a fairly simple example, but why did I choose to do that? Some of you may have already guessed that if we know that x and y are differentiable functions, and we also know that the constant functions, like we have seen in our first example in the previous slide, they are differentiable, we can use our algebraic properties to say that a polynomial. So a consequence of all these discussions is that polynomials, or let me be precise, so bivariate polynomials are differentiable. So note that these points that we have chosen as before has nothing special. So f and g, these two functions x and y, are differentiable everywhere on the xy plane or the two-dimensional Euclidean space, whatever you want to say. So bivariate polynomials are differentiable throughout R2. So now let us look at a function f of xy, which is given by xy divided by x square plus y square at the point at all points which are not origin. So here x square plus y square do not vanish, and this rational function, bivariate rational function, makes sense, or it is well defined, and we define it to be equal to 0 at the point xy equal to 0, 0. But we have seen that this function is not continuous, and we know that if a function was differentiable at a point x0, y0, then that function is going to be continuous at the point x0, y0. So if it was true that if xy was differentiable at the point 0, 0, then it would have been continuous at the point 0, 0. But we have seen before that this function is not continuous at the point 0, 0, and as a consequence it is not differentiable at the point 0, 0. One last example, let us look at this function if xy equal to x square plus y square. So we have seen, we have dealt with this function before as well, and it turns out that none of the partial derivatives fx and fy exist at the point 0, 0. This we have seen before. So let me just recall how do we check this. So what is fx 0, 0? Fx 0, 0 is same as limit h tending to 0 under root h square plus 0 square minus 0 divided by h, and this is equal to limit h tending to 0. We are always going to take the positive square root. This is modulus of h by h, and we have seen in our single variable calculus that this limit does not exist. So does not exist. So now we have seen in our previous video on differentiability that if f is differentiable at a point x0 y0, then if x0 y0 and if y x0 y0 both exist. But here we have seen that if x0 0 does not exist. So if f was differentiable, then both of them must existed, but here we have arrived at a contradiction, and as a consequence f is not differentiable, f is not differentiable at the point 0 0. So this finishes our discussion, at least in this video. We will come back with more and more on multivariable calculus in our next videos.